the real problem with Windows is that it's generally used by people who are not very smart. And out of those people come the group of Windows hackers. And so you generally do not, in public, get to see the best of the best sort of exploitation techniques. It's still relatively immature in terms of exploitation in the wild. But I just list a few things that are not basic, just so you can see that there is some space to explore in this area. Fixing a heap after an overflow occurred, when a heap overflow happens, and then you connect to it, and you want to make Win32 calls in your shellcode, it becomes very difficult because some of these calls actually do things like malloc and free, and unless you've repaired the heap, they're going to fail, presumably not in a way that you want. Finding good locations to overwrite, I think there's a lot of well-known locations for function pointers in Unix, and especially Solaris and Linux. In terms of Windows, it's a big gray ball. Some people use exception handlers, some people use function pointers they know about. I tend to like DCOM handlers, but everyone has their own take on that. Multiple overwrites, I think Brett Moore, is a New Zealander, has been pushing a few exploits around circles where he actually does multiple overwrites with your standard heap overflow. Well, what do you do with that is then the next question. So I think a lot of these sorts of issues are still being explored. Switching to the next slide is going to take a little while, apparently. Okay, so I think some of the other things are writing shellcode. I think probably about 2 years ago, people all realized you can parse the portal executable header, or perhaps more, depending on how smart you are, and get the address of load library A and get proc address, and from there you can write very reliable, portable Windows shellcode. It still tends to be rather large, but at least it's not going to rely on service pack or special function pointers. Library call redirection, because you're going to be doing Windows, you really don't have a system call interface. You need to interface with the library calls and be able to do this dynamically. And of course, the big Achilles heel of Windows has always been their use of tokens and multiple security contexts within a given process, which is a retarded idea. And I'm sure they're learning this slowly. But every Windows server is the same thing, really. It just threads off, impersonates a user based on a username and password, or perhaps if you're using SSL, it goes to LSASS, and it'll ask LSASS if it can have a token. And it impersonates it, spawns a thread with that impersonated token. And now for all rights and purposes, the actual thread is running as someone else, which means that when you compromise the thread, you have multiple security contexts to play with. You have your own, you have that of the primary thread, the main primary token, and you have that of every other impersonated thread in your process, all sharing the same data space. So this is not wise, but few people understand it, including those at Microsoft. DCRPC exploitation, DCRPC itself, no one understands. I don't think anyone in the world actually understands that protocol, which is great for us because we live in the cracks. But in terms of if you're trying to secure your system, then it's probably not the best. And also Unicode string exploitation, as OS has become more Unicode friendly, they're going to definitely have different filters and stuff applied to them. It's in bold because that's the one we're going to look at a bit today. Okay, so Unicode string exploitation. Here's the problem, which I think is common to Windows, not so much to Unix, but still in Unix, which is that you have a process, and I have IIS here because it's the quintessential Windows process, but any other server will do, and it tends to do something very similar, which is taking a string from the network, convert it to Unicode, and then pass it over via RPC to a different process. In IIS, they do DLL host, right? There's a DLL host process running around with all the ASPs loaded, or all the DLLs loaded, like ASP or anything else that you have enabled. And so the actual overflow can occur in a process that doesn't have any socket handle for you to steal, in case you want to steal a socket handle to maintain a connection, and doesn't have your original string in it anywhere, because it all got converted in the first process. So, and I think probably there was a lot of confusion because initially when Unicode started becoming very popular, people would call anything that had anything to do with Unicode a sort of Unicode-specific exploit. And then you could go look at it, and they were using maybe one string in memory was Unicode, but there were dozens of strings everywhere that were not. Or instead of Unicode, it was actually getting pre-converted on the client, and the client was sending a Unicode buffer. And this is what happens with, say, the locator bug. Right? You send a Unicode buffer over, and it copies with WCS, copy, stir copy, or whatever. But you get to control every byte in the string, which is not a difficult filter to pass through. Okay, so we are going to say, you're going to have to take my word for it, that Unicode is very popular in places that perhaps you don't know about. And as all the low-hanging fruit get picked off, people are going to use the actual protocols that Windows supports, which natively Windows is sort of very, DCRPC is kind of the backbone of Windows. DCRPC uses Unicode. So they're going to use the backbone of Windows to do their transports. And it's not always possible to use cutesy tricks to sort of get to that back-end process, 3 processes down the line, where the actual overflow is going to be. And I think Code Red, the %u trick was a breakthrough. We can actually specify any kind of data we want. But that's not always possible. So I think that is why this presentation tries to concentrate on these sorts of things. I wanted to look at the NTDLL bug, since no one seems to know what it is. You can't use the %u stuff with the NTDLL bug. It's just a Unicode string. But you can specify a string that does overflow a return address. And it's of this format, which I'm going to just, AA and BB are just 2 numbers that you get to specify. But the zeros are inserted in the conversion. And it's actually a pretty nice entry to Unicode exploitation because the overflow occurs directly in init.info, which means you're running a system and you have the socket handle and you have a lot of other stuff in memory that you can look at. And it's a big process. And unfortunately, in at least the US build, there's no text segments that are mapped to nice areas. And most solutions just guess and jump into the heap. I'm going to hit escape. OpenOffice is going to have a little chew down time. Okay, so this is the first demo. I just want to show you the WebDev exploit, which I've written for Canvas. And there's going to be a few differences between jumping to the heap and the way this does it. Cool. Canvas is this product I sell. It's cheap, but basically it's a little Pi GTK GUI over some exploits. One of the exploits is the WebDev exploit. And to demonstrate what's going on, I'm going to log in and load up OllyDebug, which is, in my opinion, the best Windows debugger for writing exploits in user space. That was fast. This is a Windows 2000 Service Pack 3 machine. It does not have the WebDev patch on it, although there's some fun things you can do even with that patch on it. So those of you with Spike can feel free to explore. But it also has Microsoft Content Server loaded on it and SQL Server, so it's going to be slow and chunky. OllyDebug is free, and it's freely downloadable, so you can Google it now. It's not open source, but you can't have everything. That looks like init.info. So it loads up all the DLLs. We're going to maximize the VMware image soon so that you can see what's going on. What happens is I run the exploit with Canvas. The first time it doesn't actually work. I have a small bug I'm fixing. And the second time it goes through and actually does exploit the target. But we're going to look at that a little bit closely. Not too closely, because I know a lot of you don't have x86 experience. All right, so the option I picked here, if you can't see it, it says I have multiple versions of the exploit. One is just a specific jump to the heap location for Windows SP3. One is do a brute force, which occasionally has the unnecessary side effect of shutting down the remote web server. Oh well. And the third version is a much more reliable sort of jump location, and that's the one we're going to be showing you. The remote target is 192.168.166.55. And like I said, the first version is just going to give us a bunch of little error messages. And initialize a bunch of DLLs on that side. And then it's going to spend a few seconds sleeping, and then it will disappear. 5 seconds. So that's kind of, we're going to start off with this demo, and then we're going to kind of jump into the, you can all read ahead a little bit. We're going to jump into the sort of what Unicode is and how to escape the kinds of problems you see with Unicode in one particular way. And we're going to kind of analyze a content server exploit. But I wanted to show you this exploit as an example of something that people have been calling a Unicode exploit, which is actually really not. All right. This time it's going to break. We're choosing option 3 again. You can see it's having a good time over there. Cool. Can everyone see that? It's nice and big. All right, so this is what OllyDebug does when an exception happens. You get a little yellow button, and you can see this. This is the stack over there. This is the sort of data window where you can change displays. The top is the current threads sort of decompilation or disassembly. And over there are the registers, if you can read them. So if you look at the stack after the overflow, you see a bunch of, these are pointers to our string, which I've set up. And this is the magic place. Right here, there's a pointer to, in the way Windows works, in C++ you say try and then catch. And the way Windows does that is it pushes first a function pointer and then a pointer to a list to another function pointer. This is called a exception handler record or something like that. So the SE handler itself is basically a function pointer that's sitting on the stack, which was a great way to escape early versions of their stack canary. But nowadays I think they've probably fixed that. So basically all you have to worry about is this is basically the return address that we've overwritten, even though really what we've done is overwritten an exception handler and then gone all the way to the end of the stack, which we're overwriting, until an exception is caused by a segmentation violation. So we can look at what's in 5e4f, and you'll see this nice call dword pointer ds eax. Right? Does everyone see that? Now, the benefit about this is the NTDLL bug is triggerable in about 80 different ways. There's a billion ways to kind of get control of NTDLL's bug here. Unfortunately, most of those ways don't get you anything in EAX. But if you use the right way, the magic Dave way, you actually do get EAX pointing to your string, which then gives you a nice, reliable way to take control. And I think we can You don't see EAX pointing to string right now because the exception handler moves all the registers around. And I think probably Service Pack 4, there will be no registers pointing to anything. I think Microsoft is going to try to fix that in a little Band-Aid. They love the Band-Aids. So that's how to write a semi-reliable US build of this. And there's actually one at 004E, 004F, and 005E, 004F. So I can't take complete credit for this sort of technique, but again, Brett Moore kind of clued me in on this call EAX, and now it's kind of become semi-public knowledge. So we can hit Shift F9, and it says I can't connect back, so it's going to have some fun. It does not, for some reason, like this particular version. All right, let's go back. Only we have the bottom of that screen. Cool, huh? This one? Not this one.
That's pretty awesome, actually. You can really see everything you're doing like that.
Sorry.
A little slow, though.
I'm trying to make it faster. Actually did crash. Killed the wrong one. Alright, so we'll get back to, now we're going to delve into the Microsoft Content Server vulnerability and how it's different from how easy and fun that one was. Which actually probably worked in the background there. It always causes that one exception. Alright. So, a vulnerability comes out from Microsoft, I go look at it because, well, now it's my job, but also because it's fun to hack into Microsoft machines. They're unwitting participants. So, August 7th, 2002, I don't know how to pronounce his name, so I will not try to butcher it, but this announcement came out, along with two other ones which are actually easier to exploit and we're not going to go over. This is kind of I said, yeah, this will make a good 5 minutes, and it turned into 2 weeks. But had some interesting notes in the announcement, which is always, the notes in Microsoft announcements are basically misleading by design, and usually incomplete, and sometimes just blatant lies. But one of the things that they do have to release something somewhat resembling the truth occasionally, so you still believe it, was that there is a buffer overrun in a low-level function that does perform user identification. That much is true. They have a little CAN number. And they have mitigating factors, which is when they start lying. And like URL scan, which blocks all URLs that contain non-ASCII data. Yeah, but that doesn't matter. And the overflow is not there. And they also say, the attacker will need to construct valid executable code using only ASCII data. Surely not. And I actually read something interesting in Banford's new book, while on the plane, and he says that when we captured some Germans after World War II who were involved in their encryption program, they said that they knew the Enigma was breakable, but they figured that it takes a whole huge building full of machines to break this thing. So they didn't think it was a problem, right? And that's the kind of attitude you're seeing here. You're saying you need to put a whole building full of machines to make this actually a problem. And I think we all know how well that worked out. So the first trick with any of these vulnerabilities is to try to find the vulnerability in question. And occasionally you find something that's like the vulnerability in question. You don't ever know if the one you found was the one that the report is actually on, which probably means they fixed 4 or 5 different bugs with the same patch. You can usually go back and diff the patch against the thing and find out. But that's really not what I like to do, since that involves work. So I tend to do fuzzing. It's something I'm semi-known for, being lazy. And I have this program called Spike Proxy, which is a sort of web man-in-the-middle HTTPS web application thing. I'm crushing Sanctum's little market. But basically, I just browse to the application. I installed it first. That's always the hard part. and then I browse the application, and then I hit, fuzz, and then it crashed, and that's it. So the way to do this, I think it's fun when you guys go back and replicate these results, right? Like scientific method, you should be able to replicate it. Is you can take Spike Proxy, you can browse to a default content server, entry, and then click overflow, and if you've attached the right process, you'll see AliDebug break with an exception. And that process, do we have it on that page? Right. The only one that loads up that's local system and is related to content server is a security service. So you already know the process when you go into this. So the request is thus. Basically, they have a domain, they have a list, and they have all these things that you send over HTTPS. And that long OAG4CA thing is actually my username for the machine. You have to have this WinNT stuff in front of it, otherwise it doesn't break. But if you put a long domain name, then you will in fact cause an overflow. And that's that. And there's the page, so now you know. Okay, what's the bug? The bug is this. This is a AliDebug stack backtrace. You can see it does a WCSN copy. You can see where the destination is. That's a stack address. If you've played with Windows long enough, you can see kind of what a stack address looks like. Heap addresses tend to be something like 007 something something or 12 something something. So, and obviously there's multiple stacks because it's threaded, but this just looks like a stack. And then you can see that you have control of the string, and that the length is extremely long. The length is 40,000, which is what the fuzzer decided to do. So this is what they did. They did a copy, and they used the size of the source, which was fantastic. Must have been during one of those lectures when they pointed that one out. Okay, so this is what I wanted to show you, like a brief summary, a one-page summary of all the other talks you've been to on Windows exploitation, where you have this SE handler, which you overwrite with something, and then you go to a jump EVX or something like that, and you get control of the instruction pointer, which then lets you jump yourself, and you have all sorts of fun. But here's one in a security service. Originally, I thought you controlled EDI, which is a register on Aitel. If you're not familiar with that, you're going to be lost for a little while. That actually is not the case. You don't, in fact, have EDI, unfortunately. If you can see down in the slides, it's probably more interesting stuff. Okay, so this been foreshadowing for a little while. It's not a typical overflow. No Windows overflow is really typical. There's some that are easy and some that are only moderately hard and need most. Various versions of your attack string do exist in memory. Unfortunately, they're all Unicoded. Also, unfortunately, on some service packs, they're Unicoded in one way, and on some service packs, they're Unicoded in another way. And this particular VMware box is Service Pack 3. In Service Pack 2, the problem is actually harder. So I was originally doing Service Pack 2, which was really painful. Okay, so here's, as you write an exploit, the philosophy of how to write an exploit is really what I'm trying to show here. It's you catalog your situation when the exploit happens. And if you're really, really good, you use the whole API of the program. Everything you can send to the program, you kind of look at in terms of how it affects your exploit. Like what kinds of memory can you move, can you change, where can you put other things? I mean, you don't have to send your real shell code in the same packet that you send your attack with, right? In this particular case, I do, but a lot of exploits don't. So that's kind of the philosophy. And I wanted to say, these are the catalog things that you have. You kind of write them down somewhere. You're like, we have this string at this place, this string at this place. We have this kind of filter applied to each one. They're converted in this way. This is what EIP is. This is how the stack is set up. And this is what's in various pointers. And then you start saying, well, what are the constraints that I'm going to have to pass through on this exploit? And in this case, you're like, well, I definitely know, and after playing with it for a little while, you realize you really can't get around the unicoding of this string. And there's a lot of things you cannot do. And one of them is you you can write EIP over, and that's fantastic. But you can only write it over with this sort of pattern, this 00A, 00BB pattern. And they must be ASCII printable strings, and they must be, they can't be zeros, obviously, because that would end the string, and they get converted in this very annoying way. And in addition, because of the way you even get into this function, you can't use an @ sign, and you can't use a slash or a backslash or any sort of those. And the %u trick does not work, and changing the language of the HTTP request did not seem to do anything. So, for those of you who have never heard of Unicode or UTF-16 or any of these standards, you can download some fairly confusing RFCs and stuff off the net. And I actually will probably post soon this little show Unicode, which just does it real simple. But basically, it's just adding a 0 to the front and restricting what you can put in. And in addition, in some conversion routines, they also change things so that if you have an OX80, it gets turned into a OXC2000110 or something like that. So sometimes you have one byte of entry and you end up with 4 bytes. Well, you always end up with 4 bytes, but sometimes they tend to be quite odd. Well, you end up with, anyway, you're seeing where I'm going. So with that said, in some versions of the conversion, you don't end up with this C2 stuff. And in Service Pack 3, you never do. You always end up with 00 something something. Okay. So this sort of restriction on where you can return to really kind of channels your efforts. And you can play some games by trying to overwrite only 2 bytes of the function pointer, and that can do some fun. But let's restrict ourselves in the way we think about this exploit to make it more reliable. Just to cause the exception immediately, which means you're going to have to overwrite the entire return address, or the entire function pointer that you're overwriting. So even if there was a nice little call EBX or jump EBX, because it turns out that EBX is what ends up pointing to your string. Even if something like that was really nice and existed somewhere we could go, the buffer is actually corrupted as it gets processed in memory. So the beginning of the buffer, which is very common with a Stack Overflow, is trash. There's all sorts of variables there that someone actually wanted to write into. And the place in the heap, since you can throw like megs and megs at this problem, but for the sake of this demonstration, we're throwing 40K at the problem. And in the heap, where we've thrown it, we have one version of the string. So you can say, hopefully at 0017, 0001, we have one version of the string. And we can execute some instructions, but it turns out this bizarre UTF-16-ish string is very difficult to do without knowing that some register points directly to a known position in your string. And someone came up to me before the talk, and this happened before, I guess, a lot of people's talks. They're like, well, I have a way I released 2 weeks ago that you don't need to know about the position of a register in your string, or position of your string relative to a register. But, okay, I don't do that. So I'll have to look at that and see what else it adds to your restrictions. So this is in any Unicode exploit, you have to know a few things. And you want to, actually in any exploit, you catalog all the things you know. And in this case, you know what registers are writable addresses. This never changes. I mean, they're pointing to different writable addresses, but they're always pointing to a writable address. And you know what registers are pointing to your string and at what offsets. So, I mean, immediately you can see the inputs to make Unicode 2, which is going to be output of this whole exercise, which is a function that generates shellcode. And hopefully you have the slides in front of you, but if you don't, basically there's classes of instructions that you're then going to use to generate an encoder or a decoder. And that's kind of your 1-byte instructions. So like 41, we all know, is inc EAX, and 42 is inc BCX or something like that. But yeah, I know a lot of you haven't memorized. You're all laughing at me now. But you have like 1-byte instructions that you can use, 2-byte instructions that you can use, which are going to start with 0, 0, and then a number, or have a number and then 0, 0. And then you have 3 bytes or 4 bytes, and if you look at your slides, it's kind of showing you the little restriction you have. Basically, you can use anything that has anything 0, 0, sometimes 0, 0, something. So, obviously, Canvas has a lot of, I wanted to stop writing Windows shellcode at one point until I realized you're always going to be writing shellcode. You just have to live with that. It's like a drug regime. But, So the canvas does a lot of things for me, and one of the things I want to do is be able to use this shellcode in every other Unicode exploit that comes out, because, like I mentioned before, I have the profound belief that there will be more of them. And I also, on this slide, just have primitives that we're going to use to construct it. So you think of yourself as an assembler trying to construct, arbitrary data, and these are sort of the primitives that you can call. You can say, I want to move between registers, I want to add and subtract contents from registers, and I want to move between registers and memory. Right? If I can do these things, I have a little machine that I can write. So this is what the finished exploit does, and I want everyone to see where we're going, because I think a lot of these talks, you kind of get lost in the middle. You're like, okay, why are we doing this now? And don't do that. Okay. So this is what it does. Basically, it overwrites the exception handler, you jump to the heap. Once on the heap, you run a little increment EBX thing, and you actually can only do that because you know ESI is writable. We'll get to this sort of stuff later. And then you jump to sort of another decoder, which then jumps to another decoder, which jumps to another decoder, and eventually you're actually executing something worthwhile. So how do we get control of EIP at a known place in our buffer? This is earlier on where you want to know that a register points to you, and then you want to get control of EIP and still know that. And EBX does point to a known place. It points to a known corrupted place, but it does point to a known place. So what we're going to do is we're going to increment EBX, and then we're going to push EBX, and then we're just going to return, because you can do this relatively easily. And the other problem you have is that you need to align yourself with, because you have zeros interspersed in your thing, you need to be able to execute both 1-byte and 2-byte instructions, and 3-byte and so on. You're very carefully maintaining what alignment am I on. I need to execute some sort of no-op to realign myself as I execute this code. So here's a magical alignment program, or code. Basically, 26 has no effect on itself. So 260026 and 0026 will all end up executing exactly in one alignment. Can everyone see that? Kind of just aligns you. You jump into a bunch of these no-ops and you become aligned. Okay, and then, if you look back there, that does say ESI has to be writable, because it does it right. Okay, so I wanted to give you a quick look at this. I think we're going to skip a couple slides here briefly because we're going to do a demo that kind of demonstrates a lot of this. But so you have this sort of no-op, this 26 no-op, and you have 6E, which is actually going to be an alignment thing. And then you're going to increment EBX. And then you're going to have another alignment, and then you're going to increment EBX. Because you can't control that these zeros are there. Those zeros are going to get put in there for you. So even though your string originally was 26, 6E, 43, 6E, this is kind of what it actually does. And then once you go through that. And then it turns out that the string that you're actually executing in got encoded in a certain way, and you can use a non-ASCII printable character, C3, to return. Even if you don't, there are other ways around this. And if you have the bottom of this, then you can see it. But, okay, so we're rationalizing here, and we say we know EBX is pointing at our string, but it points at a place that is crap. So we need to increment it. We've done that. We've seen all that. And we've solved the problem of not knowing exactly where in the heap we are, because the heap moves around willy-nilly in Windows, especially in processes that you don't really control. And so, maintaining a model of the heap is going to be a big pain. So we don't really know where in the heap we are, and the no-ops align us and take care of that problem. Okay. So now we're jumping into shellcode. We have execution at a place we know enough that we can actually do the exploit. And we need to write this encoder decoder. And the basic concepts were originally taken from Chris Anley's paper, which you can download from his website. But he actually uses a bunch of characters that we can't use. So we had to change a lot of that. And here's how I wrote this decoder, which is to create this little loop, which actually is not a loop because it gets completely linearized. And it kind of just adds this button. You can see the instructions that it does. It uses these primitives, which in the program itself are a dictionary. They're a hash table, if you will, of sort of the instructions that you're allowed to do. And so it sort of assembles it as it goes along. And what you're doing is you're maintaining sort of one register as a counter, which is going to be your data that you're going to put into memory, one byte at a time. And at the other end of, at kind of the other end of your string, you actually have a big block of sort of pre-printed table. So you get control of so many bytes. The major problem with this is size. If your encoder is too big, it's just not going to work. And it does get really large. So line on a line, we've all worked through. Started out with pushes and pops, which you can all see. We want to do also, one of the primitives that I missed in the original list was setting a register to a known value. And this is how you do that. Push it and you pop it. It's all very standard. So I wanted to show you kind of what the shellcode looks like. This may be a little hard to read on the screen, but basically it subtracts a known value from EAX, which has already been set. In order to set EAX to something you know, you then kind of, you also have to walk a pointer through memory, so one of the pointers is your encoded or decoded shellcode. And at that point, you kind of add what you're pointing to what you have. So if it's a 0, you add whatever's in AL to 0, and that's going to be the value. But if it's not 0, you have some options. So you can try to play little games with the actual stuff in memory to optimize the size of this encoder. So the issues that you're looking at, Windows shellcode, parsing that PE header like I mentioned, and I think LSD has some public code that does that, and Greg Hoagland has some code that... No, Greg Hoagland's code is a section handler, isn't it? I'm not sure what his code is, but it's been out there for a while. You can do this PE header parsing. But the big downside is that unlike Unix shellcode, which can be 23 bytes long and still be great, Windows shellcode tends to become bloatware itself. And even, if you remember the original paper that started people really looking at Windows, the Dow Windows Overflows by Dildog, he was like, what are you writing, an MFC exploit? And the reality is you're writing this giant application to the Win32 API, and it gets big. So 500 bytes is not a completely unreasonable size. And actually this is my current shellcode, because there's a bug in load library A that you have to account for, has kind of ballooned to 800 bytes. So I have a lot of shellcode that I need to put in there somehow to make it reliable. And optimistically, the shellcode is going to get 10 times bigger when it goes through this whole encoding process. But that's too big. There's just not enough space on the stack. And stacks, even though they tend to be similar sizes, they're not always the same depth, basically, if you think about it. And you don't know that you're going to have enough room for that. And you can only subtract or add so much because you can only use certain characters. So sometimes you're playing wraparound games with EAX to try to get it to be the right value. You can't do certain numbers like OX40 because you're not allowed to use an @ sign in the string, or 5C, 4C, or any of these. Anyway, so I have this on my, if you go to my Canvas webpage, which is immunisec/Canvas, you can download a nice new version of Make Unicode 2 that you can run with any Python, and you can convert any shellcode into this nice format, which we're going to do a demonstration of soon. So the annoying thing about this is to crush this down, crush it down even farther, you have to write a second stage, which is going to actually go search through the heap and find your real shellcode, decode that, and then I have another decoder on top of that, which runs the shellcode. And this makes it all a big fun game, and you're playing games with the sizes here. And as you stage up, you're in a bigger space, so you're kind of growing and getting bigger and stronger like the Hulk. Okay, so you're never just screwed. And this is the important lesson that the Microsoft technical writers know but don't want to know, which is that it always eventually does work, even in bad times, because sometimes you really want to get into a content server machine. So we'll do all the things we have to do. And we're going to start at 1701 because that's where the heap is, and we know that we're there somewhere. Okay, so if you've gone through this whole process and you've gone, I mean, this took me 2 weeks, so you're getting a compressed thought process. And I've tried a few other things. But the decoder and all the decoders are going to go hunt through the heap and find the actual shellcode and eventually return you a shell. And after this conclusion, we're going to go do the demo. So don't fall asleep quite yet. But I think the main thing you can learn is that UTF-16 should not be a problem for you if you have some spare time on your hands. The exploit has one hard-coded value. In Windows, this is considered decent. Embarrassing, but still decent. And it's easily adapted to other overflows of this type, which I believe there are many, but that remains to be proven by the public, at least. And you can find, this is my webpage. If you don't know how to find me, you can Google me or find some other way. But that indeed is where it is. That's my pretty picture. Okay, now we're going to do some demos and do some ollie debugging. Yeah, you can see that it actually did work. I'll show you just how Canvas looks when it's actually working so that you can know when I'm lying during my presentations. But when the WebDAV exploit ran, it actually did the overflow, caused a little exceptions, did some fun things, and then connected back to this other machine, which is at 192.168.166.1. And at that point, this little listener popped up. And you can do things like upload or download files and run commands and PWD and that sort of thing via the shellcode. It does whatever it has to do to get that working. So that's what happens when it works. So now you'll know if my demo isn't working. We have to close the WebDAV thing because IS must die for can't have two exploits exploiting IS at the same time. So if your exploits don't work in the wild, that means I'm busy. Come back in 10 minutes. I'm going to give IS a little bit of time to start back up. Okay. I only have one version for the content server exploit. It's more technology demonstration than anything else. All right. All right, so I used to think this was a one-shot, and by that I mean one that you would only get one chance to try it out, and then the process would die, and you wouldn't be able to get in. But for some reason, it's not on SP3, and it gets restarted nicely every time you try the exploit. So that's adding to the reliability of this exploit. So we're going to attach to it. So typical ollie debug behavior, an access violation has occurred, we're going to get control. Cool. Okay, so this is what you're faced with when you actually do the thing. And it's a Unicode string. Ollie debug is great because it tells you what pointers are referenced and kind of prints them out for you. And initially you're like, well, EDX is pointing at me, and ESI is pointing at me, and there's a few other things pointing at me, and maybe it won't be so hard. And you kind of do a search looking for other versions of your string, which I'm not going to do now, but you can load up the memory map and do a search, and you won't find any versions of your original ASCII string. And this is when you start going, maybe not as easy as I thought. And if you look at the stack, you can see all the Unicode stuff, and it hit the end of the stack, and that's what we're actually seeing here is, I hit the end and I don't know what to do. But somewhere above that, hidden in the mess, is the exception handler here. Okay, so at a known place in our string, the exception handler pointer is going to be. We don't really care about the next record because, as far as we're concerned, there is no next record. You don't return from this. And that right there is the address we're going to go to. I'll show you what it looks like in the dump. It looks like this. And even if it hadn't been perfectly aligned for us this time, if it had been like, if we go to 170002, you'll see that it doesn't matter because in the end it does get aligned for us. And you spend a few while hunting down through the shellcode. Past it at that point. Heap shellcode does get corrupted, but it doesn't seem to matter to us because there's just so darn much of it. Should be doing a search here, but I always thought this was faster. Turns out it's not. All right, here we go. All right, so here you're seeing what we do. We do a bunch of 6Es and 4 3s, and there's just a list of these things. So in the actual encoder, what you do is you specify, I have EBX pointing to my string, and I want to increment it by 17 and put that in here. So there's actually a whole demonstration for this particular exploit in the code I gave out. And at the end of this, it quite nicely just returns, push EBX and then return. So I'm going to put a breakpoint there. And usually it winds in plain. And we're going to hit Shift F9, which is how you handle the exception. And hit the breakpoint. And you can see now, if you do a look at EBX, which we're just going to F7. Okay, so here's what happened. This is the shellcode. Now we're executing the shellcode on the stack where we know a pointer is pointing to, and we know exactly what instruction we're pointing at. So we have a push EBX and then a pop EAX, which is going to say, it's basically move one register to another register. And in between that, you have a 3-byte no-op. So you can immediately see where all the length problems are coming from. Because every time we want to do a simple primitive, we have 10 bytes or 7 bytes or 6 bytes, however many bytes that is. 5? All right. So, I mean, that simple primitive takes 5 bytes. Some other primitives take other amounts of bytes. And I'm going to walk through briefly to show you that, now EAX is pointing at a certain place. We're going to add to it because in our string, at the end of our string, is going to be the sort of mask that we're going to apply to the shellcode. We're going to subtract to it. You have to kind of add and subtract and play with it. We want to add OX500. We have to add and subtract because you can't have a 0 there. Move some registers around. We're going to set EAX to a certain value. You can see EAX just changed into a value that we know. And we're going to start manipulating. In this case, look at, I don't have a laser pointer, but look at the AL, basically. It's the EA in this case. And you can watch that. That's actually the number we're going to be putting into our shellcode to decode it. So you can watch it as it goes down. In this case, 8B. And we'll show you what's getting decoded here. That's not it. Yes, on. That's not it. I'll step a little bit. All right. Add to VCX. Okay, so you can see this is the mask. This is the sort of shellcode before it's been decoded. And you see all these ones, which are basically just placeholders. And then in some case, the zeros are there as well. And we're going to watch this kind of step through and change that shellcode to be what we need it to be. Where you see, say, a 7.4 or a 7B or something, the encoder realized that it could save some space by just skipping that particular byte because it could just put it in there. So as we step through, you can see it kind of changing what that shellcode is, and it's disassembled here. So that's the actual, what you're seeing over there in the disassembly is the actual search code. It's going to search through the heap to find the other code, and it's going to decode that with a nibble encoder. So you can see the bytes scrolling by as it does this, which is a problem. Ideally, with an exploit like this, you should have multiple encoding options so that you can, if one doesn't happen to work, you have another one that may. Perhaps one's too big,